Hello and welcome to another of my videos. And I must confess, this is a little bit of a vanity project because Frame was a computer system that I looked after for about 20 years. Um, and sort of got a place in my heart, if you like. So what was Frame? Well, Frame was British Rail's signalling failure recording system, or one of a generation of them. Started in the 80s and ran into the early noughties. So if we go right back before Frame, there was a system called SATIS, Signalling and Telecommunications Information System, and that was quite a large system that captured financial information. It held the equipment catalogues, and also it recorded information about signalling failures. And this was a mainframe-based system, uh, and had lots of dumb terminals for access to it, and produced standardized reports, often that you had to wait for arriving in the post. So Satis was around in the 1970s, early 80s, as I say, based on a mainframe system, mainly written in COBOL, I believe. So what was the process back in those days? Well, technicians went out and repaired a fault. I'm sorry, I couldn't find a picture of technicians without high vis and hats and everything, because back in those days, health and safety was a little bit different. Anyway, having fixed the fault, the technician was then expected to fill in a fault report form, which detailed when it occurred, what had happened, what had failed, etc. And those forms, if they were written, and of course, if in that time the technician was responsible for both maintenance and faulting, if it was actually something that they had done or not done maintenance wise, then sometimes the fault reports didn't make it through to the supervisor. And the supervisor would sit in a typically smoky office, and would check the forms and annotate them with more information about what the underlying cause was. And that would then go off to the divisional or regional office. However, of course, um, if one had KPIs around failures or numbers of failures on your patch, then quite a few of those forms could end up in the waste bin, particularly if they weren't completed by the technician and the supervisor couldn't be bothered to find the extra information. So our form has now made it to the regional office where it's going to be entered into Satis. And the first thing would be for a technical clerk to add coding onto it. You don't want to put plain text into computer systems. And certainly back in the 70s and 80s, when memory and data storage was extremely expensive, you would try and code everything. So the clerk would write a series of codes on the form, to indicate the type of equipment and the nature of the failure before entering it into a dumb terminal linked into Satis, which would then take the information, check it on the mainframe, and then indicate success or failure back to the technician. But most of the information that was entered disappeared into what could be called a black hole. An awful lot of information being entered, but the ability to get it back and to use the information was quite limited. There were a few predefined reports and some predefined statistics. So was it an efficient process? Well, if you went to the regional office, and I experienced this in York, you'd find that the technical clerks would have an in-basket full of fault reports that had come in, and they would be busily coding them, and they would be entering them into the computer system. But of course, while they were doing that, the post would arrive with a whole load more fault reports, and the in basket used to get bigger and bigger. And at York, even with two clerks, Annie and Ray, working on it pretty intensively, they still had to come in on some weekends to do a Saturday or Sunday shift in order to catch up with the backlog, particularly if any of them, either of them wanted a holiday. So, what were the challenges of that system? Well, it was the time it took to process a form, and that was, of course, if the form even reached the regional office. There was the opportunity that people would make errors in coding it. They had to read the information, often in poor handwriting, interpret it, and then write down the code. And of course, they would learn the common codes and would have to look up any others. So there was a chance that one would put in a code that you knew. There was very little feedback on actually what was happening. There was some information that came back from the system, but it was hard to understand what was changing, what the poor equipment was, and the like. And I think it was pretty soul destroying. I was pretty impressed with how the people in York kept going, even when it was garbage in, nothing out. Oh, sorry, data in, nothing out. So around about 1985, it might have been 1984, memory is a little bit rusty, Frame was born. And it was not me that generated it. It was a guy called Colin Dowman on the southern region who started to provide an input tool designed to speed up the entry into the system so that you could type the fault reports into an IBM PC, which were just starting to be deployed on British Rail, and then that could actually do some checks on the coding before it then sent a batch of fault reports up to the mainframe. The same sort of time, other people also on the southern region, and I think Jim Debray may have been one of them, uh, was developing a tool to take the information that the mainframe could return as data files or as reports and use that to analyze the data and allow for more interesting analysis. And the very early tool was initially written in DBase 2. DBase 2 was a commercial database language. It was quite powerful for its time, but it was very quickly overtaken by DBase 3 and then DBase 3 Plus, and there are other clones called Foxbase, and there was one called Diamond as well. And having upgraded to those later versions, then a system could be provided which enabled good, efficient inputting and analysis of the data. So the world was changing and fault controls were considered. So very early on in my career, when I started, maintenance and faulting was combined into one activity. Technicians were allocated to an area of the track, and they were responsible for doing the routine maintenance and checks, but also responding to any of the failures. The signaller would contact them or wait for them to turn up if it wasn't important, and then they would be detailed to deal with any failures. And that was being changed in order to make it more efficient, or so it was thought, and particularly as the emphasis was going towards dealing with failures quickly to keep trains running, technicians were split into two groups, with some dedicated to maintenance activities, covering larger areas than previously, but routinely going around checking points, signals, track circuits, etc. And then roving fault teams who could be called out 24/7 in order to deal with any incidents. So whereas the signallers used to know the technicians and used to know which of the various depots to try ringing to find them, or they would put a message out to the other signal boxes saying, "Have you seen the technician?" Um, then they needed a different way of contacting the fault teams. And just before we go on, you may remember that large signal boxes were introduced as part of the modernisation programme, and finding technicians could become much more difficult. And I can remember on the Midland, we had a system called Cuckoos, or that was what we named it. where the signaler could send loud squawks from loudspeakers mounted on location cases down the track. And there were codes for technicians, P-way, operators, etc., to contact the signaler. Anyway, we needed a single point of contact, and so the first fault control was launched at Liverpool Street, uh, just covering initially the Liverpool Street area, but expanding out to cover the rest of the Great Eastern and on to the West Anglia and C2C lines, or LTS at the time. And one of the challenges was that we discovered that there were an awful lot of failures which were not previously being recorded. And there was something like a tenfold increase in the number recorded. Now, that was expected there would be an increase because it was known that some of the forms didn't make it to the regional office. Some very minor faults would be dealt with when the maintenance technician visited site. And so we'd expected things like first filament failures and the like to increase. But the increase was much more dramatic than expected. And initially, the fault team were swamped by the number, and we had to delay the rollout of the fault control until we could improve the resources and the processes. And because it was a new system, the way that information was recorded had not really been tried before, and there were some challenges about the input process. So whilst it was mainly Colin Dowman got on with the Liverpool Street fault control, I began to take over the input tool and worked in DBase 3 and a Diamond compiler to make it easier to use. Things like providing drop-down lists for the various codes so that the user, if they couldn't remember a code, could start typing in the textual name and then it would appear, and beginning to link codes together so that you got the most common codes associated with a previous code. It also started to store the entered failures locally, and having got a database effectively of the faults reported through an office, then it became possible to introduce search and reporting functions using that local data. And combining with the other routines that have been developed on the southern region, we got a more comprehensive output suite, enabling people to analyze failures, to look for trends, to demonstrate whether actually the switch diamond point mechanisms, which people hated, were actually worse than other types of points. So here is the main screen of Frame. This is a version from about 2004, 2000, yeah, about 2004 probably, just before it was expired, but actually it hadn't changed much since the mid 1990s. And if you logged into Frame as a normal user, in this case you're actually as an admin user, then you got a number of options, and it was a simple menu-driven system. Now, for those of you familiar with Windows and modern apps, then it may look a little bit clunky. But we have to remember this was developed when PCs were quite crude. You had an 80 by 25 character screen. There was no graphics other than the graphics characters that could be represented by, as lines and the like. And it didn't have any windows. You only had one application running at a time. As I say, there were no graphics, so you couldn't get any pretty pictures or anything up. It was quite a crude system. So having selected that you want to do an output, then the first thing you had to do was to select the data that you wanted to output or process. So we had an option for searches. As you can see, then there was options around listing the failures that had been selected. There were statistical options. There were some graphs. So having mentioned that the basic PC didn't have any graphics or facility, there were things like Hercules graphics cards that you could buy as an add-on, and some of the later PCs had an IBM graphics color graphics card as well. There was the option to store results so that you could call them back later. You could do various external things, print off other data. So if we go into the search menu, you had the option of performing a search. You could look at what search files had already been stored. You could do some various items, including something called place concatenations. So what on earth is a place concatenation? Well, each failure was assigned a place code. So there was a list of place codes along the railway. And this was actually one of the first involvements I had with Liverpool Street Fault Control, was working with a couple of colleagues to uh, identify all of the places along the Great Eastern Main Line and the branches where there were clusters of signalling equipment and it would be appropriate to assign failures to. So, for instance, you might have Romford Up Junction, South West Junction, I suppose it would be, Romford Station, and then Romford East Junction, and then you'd have the branch to Upminster perhaps as one, or possibly split between Emerson Park and Upminster. However, when you're looking at failures, you're often interested in an area, and you could be interested in not just the main line going through a junction, but also the parts of lines that join with it. Because if you have a failure of the points on the main line, it may get reported as a fault on the signals protecting that junction. So a place concatenation was a way of grouping together a list or range of place codes, and that could then be searched for in one activity, rather than having to do a search for each individually and then combine the results. So when you were doing a search, then the system actually allowed you to select data from all the available data, such as your failures and monthly records of failures, or from previous search results. So you could take groups of data, select information from it, combine them together by using them as together as source files, and then do further research onto them. And the search criteria was quite extensive. Almost anything you might like to analyze in the data, you could search for. Obviously, the date of the failure was quite a key item, and you can see that it defaulted to the 1st of the 1st, 1984, which was when the earliest data was available. Uh, Time, you could do days of week if you're interested in weekday failures or weekend failures, how long it took for failures to be attended to and repaired. And there was also an option to include or exclude information that matched the criteria. So if you were only interested in failures that took a certain period of time, you could exclude all the others. The failures were all coded using a series of codes, starting with how the fault had been reported, which was a high-level description of the type of equipment, the system code, which was the basic equipment types like signals, different types, points, etc. And then that broke down into an assembly, sub-assembly, and component. For some failures, not all of those levels were needed and were not all completed. There was also some challenges in that as you worked your way down the detail level, then local names for items also began to affect how the system would be coded. There was then a defect code to describe what had gone wrong, and this caused some grief because if a bulb fails, then there were several codes that people could use, and different regional offices and local offices used different codes. So, for instance, a lamp failure could be described as broken, mechanical failure, as in the filament, electrical failure, disconnection, damaged. There was a number of other codes as well. So trying to select all the lamp failures was a challenge. Attribute was who was responsible, typically signaling maintenance, obviously, or signaling assets, but it could be that the track engineer, vandalism, things like that. And where it was known, then the manufacturer could also be entered. Moving on to locations, then there was the option to enter a range of place codes, and in that area you could also, if I remember rightly, put the concatenation codes. Um, you could identify by maintenance area, by faulting teams. You could look at the uh, equipment itself by apparatus name or the signal box prefix, a failure number range, and a basic root session. I'm trying to remember what the BRS stood for. But there were ways of analyzing by location. And then there was other codes as well, which could be used, including the classification of the failure. Was it a right side or wrong side failure? You could look at the impact on trains. Initially, faults were just recorded, but as we moved to fault controls and we moved into the rail track era, the train delay was also added into records. One could look at the priority that had been assigned to the faults, and where it was a telecoms issue, then you could also search for telecoms information. And there was the option to search now or search later on. Often, if you've got a number of searches you want to do, then you can set them up and then leave the computer running to do them as a batch activity while you go and have your lunch or a cup of coffee. And there was also an option to add a debase condition into the search criteria. Not used by very many people, but occasionally, if you had something really special that you wanted to look for, you could use that. And the results of each search were saved in a file. You named it and they were saved on your computer, and you could use those as the input to another search. And that was really useful because when we started to output the results and look at them, we found that if you were too specific in your search criteria, then you would often miss quite a lot of the input. As I mentioned, for a lamp failure, if you included the defect code, you might only find those which were entered at York or Birmingham or Reading, not all of them. So sometimes we found the best thing to do was to not search too specifically, but look for a broader group of failures. Perhaps just put the system code in to start with, or the system and assembly. And then to print out even just a small part of that list of records and look through them to identify the ones which matched the areas of interest, and from those identify which codes or combination of codes would be appropriate to search for. So how did you list failures? Well, the listings menu gave you the option to list and print failures, and this was a very open sort of reporting tool, very much like the reporting tools that are often available now for databases where you can create your own reports. There was also the ability to analyze repetitive failures, uh, wrong side failure reports, and to translate the core data into another DBase file so that you could use it with an external routine. So if you wanted to translate some files, then you entered the file names and you could enter up to about 12 different files, which would all be combined together and searched. In this case, I've just picked the standard failures database, which was the live data being entered. And as you can see, there were only 2 records in my play copy. You could then select which of the various fields you wanted to be listed from left to right across the report. And you can see that for something like a place, F and G, you've got the place code, which would be 6 or 7 characters, and we've got the place name, which would be typically 25 characters long. And we've got a whole range of columns that we can include within our report. And you can put them in the order that you want. They do not have to be in alphabetical order, although that's what I've used here. It was also sometimes useful to group reports by perhaps the fault team or a place. So there was the option to split the report into each change of that particular code. Also, it was sometimes useful to sort the failures into a specific order. If you're combining data from many files, they're not going to be in any particular order. So you might want to have them in date order, or in this case, in the place code order, so that they're effectively along a route. You can give the print a title, something meaningful, and then there was the option of printing it or displaying it on the screen. And in this case, we're going to display it on the screen. And here is the output. So it is listed on this particular page, the failure number down the left-hand side, and you can see 7115000001 and 2, the date of the failure, the time the failure was recorded, the place name where the failure occurred, the apparatus which was affected, and the system code as is entered in the system at the time. And because this was the live failures data, you can see the system is currently unknown because the failure has not been rectified yet. And you can scroll up and down multi-page reports. So how was it all written? Well, as I say, it was written in DBase 3 Plus, which was quite a simple language to write. And here's an example of it. And those of you familiar with things like C or Visual Basic or Python will probably be able to at least make some sense of reading it. Now, one of the challenges was that DBase 3, although it was very flexible, couldn't do certain things, and it certainly couldn't do certain things very quickly. And so if we look right at the bottom right, you'll see that there is a line that starts with C call and then has a name of a external routine, in this case repo mod, and then some variables. So the Diamond compiler, which I used for DBase 3 programs for Frame, enabled you to call routines which had been written in C or in a C equivalent language. And in this instance, having identified all the elements to go into uh, a report to be displayed on the screen or printed out, then we used a report format, an FRM file, which was a standard DBase 3 file. Now that file was normally created by the user, entering the fields they wanted, adjusting the widths, that sort of thing. But we wanted to automate it, and that was not easy unless one went into an external routine. So in this case, repo mod was a routine, repod modification, you can work it out, can't you? To take the control file temp.txt and the template report form temp.frm and to modify temp.frm in accordance with the instructions that the user had input through the menu system. And that was actually written in assembler. I didn't have access to C at the time, so instead I wrote it all in assembler, and here's a little example of the sorts of things that one could do, and that was then compiled into an object file, which was then linked in at the compiling stage of the frame program. As I told you, this is a little bit of a vanity video and a little bit nerdy, so gloss over this bit. So what about statistics? Well, there was a number of different statistical forms that have been identified by users, and that's one of the key things with Frame. Most of what was included within the system was driven by the users. A user would come along and say, it would be really useful to be able to see what times of day failures occurred. So option 5 here, time of occurrence spread. And that would tell you what time of day each the failures generally occurred. And there were also options to graph that. So DBase didn't really support graphics. Uh, Graphing was very new. Um, the spreadsheet programs of the day were one called SuperCalc and one called Lotus 123. Excel had not been invented. They had very primitive graphing facilities. Um, Again, it did require you to have a suitable graphics card. Um, so we introduced into Frame the ability to graph using various graphics adapters, including the Hercules card. And you will not be surprised to know that this was all written in uh, assembly language uh, to actually generate the outputs that you see on the screen here. Now, drawing a bar graph and shading it in different colors was not too difficult to do in assembler, but doing pie charts was a little bit more challenging. As you can see, the shading doesn't quite work, um, and the circle is not quite circular. But all of that was done with assembly language, working out the coordinates of the circle and then working out the uh, lengths of the shading so that the shading would fill the arc of the circle. Now, in this case, it's a very simple two uh, semicircles, but when you have small segments and when you explode them so that they are not all centered on this origin, then it gets a little bit more challenging. Anyway, Liverpool Street for Fault Control was deemed a big success. Quite a lot of challenges, quite a lot of issues with it. There were various bits of the process which were found not to be brilliant, and there may be some people who worked there who worked on the original fault control system who might want to make some comments on this video. But I was up in York working in the office there, had been working on the fault on the frame programs, the input and the reporting. And one of the senior managers, a guy called Quentin MacDonald, said that we were going to have a fault control at York, and he wanted to analyze the process from scratch, learning from what would happen at Liverpool Street, but actually not just adopting it because we reckoned we would have a significantly higher number of faults and we needed to be more efficient. So he set out some objectives that a fault should be recorded from a signaler on a telephone call within 30 seconds so that the signaler could get on with doing their safety critical work, and we need to record accurately what was the information. And that each fault should automatically be allocated to a fault team, and that should be broadly automatic, or at least the system should suggest the default team. The Liverpool Street system captured the faults, and then there was a second process to go and to find a fault and then allocate it to a team. For each team, he wanted the operator to be able to see a list of faults that are allocated to that team, and he wanted to be able to see them in a priority order. And he felt that the operator should be able to plan the work of the team, so they need to be able to move the faults up and down the list, perhaps to plan a more logical journey between the faults, and also to move failures to another team. The whole idea was to make things very quick and simple. So a lot of things he wanted to be done by a single key press. So if there was a fault highlighted on the screen, a single key press to indicate that the fault team had been advised of the fault, or that that was the one they were working on, and to very quickly move between the different screens using the function keys to get to the place you wanted to be. No drop-down menus, etc. Also, we are concerned that failure details were not being accurately recorded with paper reports, so we wanted an engineer to be on the call. So when the fault was rectified and the fault team reported back, that it was a signaling engineer who could actually ask them intelligent questions and make sure that the fault was accurately recorded. And there were a couple of other things that he wished for, which were a little bit of a challenge, but we've managed it. One was to be able to send pager messages. You may remember pagers if you're old enough. And so the system was able to send a message to a fault team or a supervisor using a variety of different radio pagers. And each day, the people out supervising the various areas needed to know what had failed. One of the problems of going to a fault control was that the maintenance and supervisory staff didn't know what had happened. So Quentin said, could we fax out every morning a report for each of the supervisors or each of the maintenance teams or each of the fault teams? In those days, we didn't have email, or certainly not the email that you're familiar with. We had something called micromail, but not everyone was attached to that. And most information was sent around using fax. So that was another challenge in order to be able to automatically generate reports that then could be automatically faxed to the various people without ever needing to be printed out. So how was the system devised? Well, it was based on a network and we had a server and the early servers were a 386 processor running at about 10 megahertz with a 40 megabyte hard drive. Just think about your mobile phone now. Later ones went on to being a Pentium-based servers with larger hard drives. And that was connected to a hard cabled Ethernet. Um, Various types of Ethernets were used, but after a while we went to the coax type. And each of the controllers would have a terminal attached to that Ethernet. And you could have one or many controllers all working at once. Now, obviously, with lots of people working all the time and all these various reports to be produced, you need a computer that is monitoring the system and generating all the information to go out at the right time. And this was known as the status monitor, a specific program running again within the frame suite, but selected by the administrator to run and process everything in the background. And one of the things that would connect to was another computer, which was the gateway to the mainframe. So all of the failures that were recorded locally still needed to go into the mainframe system, and also there was the opportunity to transmit files to different places. Another computer with a modem in the back was the paging computer, and this had some bespoke software which I wrote again in assembler to take a queue file of paging messages and then to dial up Vodafone or BT and to transmit the information to their server, which would then go out as a paging message to the recipient. And typically, there would also be one or two computers which would be undertaking the faxing. Sending faxes is quite a slow process, hence the normal need to have two computers doing it. We tried a number of different cards that you could use and different sets of software, but again, there was a bespoke piece of assembly code compiled as a COM file, a .com executable, which controlled the faxing software and told it which of the various fax files to send next. And as we changed to different faxing software, hence that program developed. So let's go into York fault control or Liverpool Street fault control, perhaps later on. And here is the basic screen that a controller would see. For any particular team, and they could change between the teams very quickly, then they would just show what the list of failures were that were allocated to that team. Colour was used to indicate whether teams were on duty or off duty, whether faults were new faults, whether they were being attended to, whether they had been fixed. So here we have two new faults, which are shown in green. And down the bottom of the screen, you can see a blue bar which gives some more information about the highlighted fault, when it was failed, whether the team has been advised of it, and what type of equipment it is if it's known. Below that, we've got two teams. That could be full with about 15 teams, 20 teams perhaps. And each team has got an acronym, and then below it, there were two numbers, one showing the high priority faults and one showing the lower priority faults. So we decided that we would use different types of people to respond to faults, and particularly for a new failure from a signaler. Here, it was important to get the key details down, recorded quickly, and the fault processed, and the signaler released to go off and do their other work. And that was target of 30 seconds, and we could often beat that. So the first thing was to select the signal box. You start typing the name in, hit enter, and a drop down list for you to select the appropriate signal box. You could enter the details of the equipment and then go to the place, where again you could begin to enter the place name and get a menu to select. Now, as I'll come on to a little bit later, the system actually learnt about equipment and had an equipment database behind it. So once you'd selected 54 signal, if that had failed previously, then the place and more details of the equipment would automatically be displayed, including on the right-hand side a history of recent failures. So that equipment database was automatically completed some of the details. And for every fault that was entered, it was stored in the system. And so the system would learn ready for next time, a very early form of artificial intelligence. We needed to know what type of equipment the was being reported. In this case, the operator is selecting that it was a color light signal, and then the information about the fault could be entered on in a free text box. Now, one of the important things with taking this information was for the operator to take control of the conversation. So they would lead the signaler through saying asking the questions and getting the answers. So, hello, signaler, where are you? Colchester. What have you got a fault report? Yes. What fault is? What's the equipment? 54 signal. Where is that? And so on. And what's wrong with it? When did it fail? Is it causing an issue? Is it a dangerous incident? And in this case, it would probably be a wrong side failure. How important is it? So the system here is guiding the user, the operator, to a priority 2 because there's a significant risk. It's an unprotected wrong side failure, and therefore there's the potential there will be significant delays. But that priority can be changed according to the report from the signaler. And having advised the signaler of the fault number, then it is immediately entered into the relevant team's list. And in this case, it goes at the top, is shown in pink because it is a high priority fault. So that controller who has taken the faults can move on to answer the next phone call. And then an engineer can allocate the fault to the relevant team. The engineer can call up the details that have been entered and has then options with function keys at the bottom to send a pager message to the fault team, to send a pager message and mark it as advised, where you're confident the message will get through, to indicate that the team has been advised by telephone, and other options. And once the team has been advised, the color changes from the pink purple color to a light blue because it's a high priority fault, and the controller can then keep an eye on it. And the engineers would be looking after perhaps 4 or 5 active teams. They would be keeping an eye on the list on each team, and as the team reports that they have rectified one failure, then they would allocate the next failure to them. And if something very high priority came in, they could then contact the team to ask them to stop the fault they were dealing with or bring it to a quick conclusion and move to something more important. So we ended up with a room with multiple operators. We had some responding to the signals reports. They were more like a call center. They took charge of the conversation and they recorded the details accurately and quickly. And we found that the people who had been trained to work in the telecoms fault control were ideal for this. They were used to taking charge of the conversation. However, we needed other people to look after the allocation of the faults and prioritize, and they needed to understand the railway system and typically were more experienced signal engineers, often from the maintenance or faulting field, but not exclusively. And it was important that operator who recorded the resolution, who got the details from the horse's mouth, sorry, technicians, um, was actually able to allocate the information accurately. And again, the engineers who'd worked on the tools were ideal because they knew about the types of equipment that was being described. So when the technicians ring back to say they have rectified a fault, then the controller calls up the fault, enters the various details of the time that it was repaired, when they got to site, can update the information about the nature of the failure, what was done. So we've got a narrative, and then can also use drop-down menus to record the different information about the equipment. And as we moved on and got more and more information, the system would learn what were common types of failure. So having entered that it was a signal color light multi-aspect, the next option would be to pick one of a set of perhaps 10 common failures, which would then automatically fill in most of the codes. Alternatively, the user could input the codes one by one. And once all the information was entered, then the controller could confirm that the fault had been completed by pressing F3 or leaving it outstanding by pressing F2, perhaps if there was further work to be done, or go back and edit it and undertake other options. And with a fault having been completed, it would immediately disappear off the controller's screens. And these screens were displayed using, again, you know it, yeah, assembly language to actually make the screens very responsive. So what happened at privatisation? Well, I started working on Frame as part of British Rail, and I worked on it from the late 1985, early 86 through to 1995, when I was part of the British Rail teams based in initially York and then at Liverpool Street in Hamilton House. And I had other roles, but Frame was something I kept doing almost in my spare time. And it's important to say that all the developments from that first version of the fault control at York onwards were driven by the users. People would say, it would be nice if the system could do, or instead of having to do something this way, could we have a different key sequence? And one of the advantages of not having a formal development cycle was that it was typically 48 hours from a request from a user to actually a version being implemented and available for them to trial. And effectively, we had a prototype being tested in real life. So, for instance, one of the controllers said, I've got a long list of faults allocated to a team, but I don't know which one they're actually working on at any one time. It would be really useful if I could mark it. So we introduced a feature where you could select the fault by scrolling up and down on the team list and press the S key to put a star, S for star, against a particular fault, and that indicated to the controller that was the one that the team were currently working on. And that was implemented within about 4 hours of the controller making the request. It took a little bit longer to tweak it and improve some of the functionality, but it was very quick. And then a new version was uploaded onto the mainframe, and other sites would download that and install it over a period of a couple of days. When privatisation happened, I no longer worked for British Rail, I moved and worked for a variety of organisations, but still looked after Frame. And I did that through an organisation called QTC, based in York, who were a company who were specialising in IT systems for the railway. And again, it was mainly done in my spare time. And so development took a little bit longer sometimes. And because they were doing it as a corporate event, uh, updates took more time because they had to be specified, tested, and it was a much longer refresh cycle. By 1998, Railtrack, who were then in charge, decided that they were going to replace Frame. It was not based on Windows, which everyone was using. It was still based on DOS, and it didn't really meet their long-term goals. And other companies were proposing to produce fault input systems, recording systems using the same code, failure codes, but in a Windows environment. So hence in 1998, Railtrack declared that they didn't need Frame to be compliant for the year 2000. And so hopefully this new system, FMS 2000, I think it was called, which was in development, would be in place before the millennia. Now, those of you with memories of computer systems and 2000 will know there was a problem with dates. A lot of systems only recorded the last two digits of the year. So when you rolled over to a new century or a new millennia, then it was expected a lot of computer systems would fall over. And Frame was one of those. The D-base structure didn't include the century initially. The system itself only displayed two digits of the year, and there was the potential that there could be problems in trying to sort failures in the future. Late in the 20th century, in September 1999, Railtrack finally realised that their new system wasn't going to be ready. They changed their minds, and I had about 3 months to update the system to make it year 2000 compliant. And actually, it only took me 24 hours because I knew exactly what I was looking for. Um, and it was done very, very quickly. Not that we told Railtrack that, because we charged them a lot of money because we had offered to do it quite cheaply back in 1998, and they had said no. So when they came back in 1999, they had to pay the price. And Frame continued into the next century, and it was probably finally turned off at the last site around about 2005. So it had lasted for 20 years, which is pretty good for a computer system, particularly one that was written pre-Windows. So, as I did say, this is a little bit of a vanity project. Frame was my baby. I really enjoyed working on it. It was great fun working with all the people who used it. We had some really good times discussing how the system could work, and I could list a whole list of people who I worked with on it, and we had really good times. But if you use Frame, perhaps in one of the fault controls, perhaps in one of the offices, perhaps just getting the data and processing it, if you've got any memories of Frame, then please do feel free to put them in the comments on this video. So thank you very much for watching. I hope that wasn't too boring. And if any of you got any questions about the coding systems, etc., I'll try and answer them. Bye for now.